Okay, this video is going to be on types of reactions. We are going to look at 5 different types of reactions in this particular chapter. Um, and the first of the type of reaction that we're going to look at is one that is called a synthesis reaction. So a synthesis reaction, if you synthesize something, it means that you make it, and that's basically what's happening in a synthesis reaction. So a synthesis reaction, let's see, let's grab a yellow color here. So a synthesis reaction, the general formula for a synthesis reaction looks like this. So we've got A plus B, and that's going to yield AB. Now, this is just a general formula. These aren't actual real elements, but anyhow, they are placeholders, if you will. So A could be pretty much anything, B could be anything, but the main idea is when you have A and B and you put them together, you make a new compound called AB. A real-life example of this would be something like if I had H2 gas, hydrogen gas, and I mixed that or added that to O2 gas, and the product of that is going to be water, H2O. So here H is going to be analogous to our A, and O2 is going to be analogous to our B, and once we put them together, we've got a new product, water. And as you can tell, we're not really worried about balancing these equations just yet, but anyhow, just so that you get the general idea of what's going on. Alright, so that is a synthesis reaction. The next reaction that we're going to look at is a decomposition reaction. So a decomposition reaction is almost like a synthesis reaction, but backwards. So in a decomposition reaction, what we're going to do is we're going to start with AB this time, and we are going to decompose it or break it down into its parts, and its parts are A and B. Now once again, A and B are just placeholders. They're not actual elements that you would find on the periodic table, but so you have AB and you break it down into its components. So if we use the water example from the synthesis reaction, we can take water again, we can have H2O, and we can decompose it into its components. If you run an electric current through water, you actually do get the hydrogen gas and the oxygen gas to bubble out of the water. So once again, the water corresponds to the AB. In this case, AB is our reactants, where in the previous example, AB was our product, but it's the same thing, but just backwards. So the next type of reaction that we're going to look at is a single replacement reaction. In a single replacement reaction, what happens is you have one element that replaces or takes the place of another one. And this happens one time, that's why it's called a single replacement. So if we look at the general formula for a single replacement reaction, it would look like this. If we would have A plus BC, and then that's going to yield AB plus C. So we could have done AC instead of AB. This could have been AC plus B, but you get the general idea. One thing is taking the place of something else. Here, A was by itself on the left, and if we look at the right of the arrow, A is no longer by itself, but it is in fact with B. So this is a single replacement reaction. If we were to look at something that would be a real life example of this, it would be if we had copper metal, so Cu, plus if we were to put it in silver nitrate, so AgNO3, so silver nitrate. So these are going to chemically combine, and we're going to have a single replacement reaction. The copper is going to displace the silver, so our products is going to be silver metal plus copper nitrate, NO3. So like we said, the copper and the silver, they basically just switched places. So that's a single replacement. A double replacement reaction is the next one that we will talk about. So a double replacement reaction is sort of the same thing going on. Two things are going to be moving and replacing one another. So a general formula for a double replacement reaction would look like AB plus CD, and that's going to give me AD plus B D. No, wait a minute. That's not it. So we're going to have AD plus BC. There we go. That looks a lot better. All right, so here on the left, A and B were together. If you look over on the right, A and D are now together. On the left, C and D are together. And if you look on the right, now B and C are together. So a real-life example of this would be if you had, let's say we start out with lead nitrate, so PbNO3. Lead in this particular example has got a +2 charge, so we need to put parentheses around this polyatomic ion and put a 2 because the charge on nitrate is -1. So, and then we're going to add that to sodium iodide. So the charge on sodium is +1, the charge on iodine is -1, so it's just NaI. So when we mix these two chemicals together, we're going to have a double replacement reaction. If you look here, lead is going to be where A is, nitrate is going to be where B is, sodium is going to be where C is, and I is basically where D is. So in our products, we're going to have lead, which is no longer going to be with nitrate, but we're going to have lead iodide. So the iodine here has a -1 charge, and the lead still has a +2 charge, so it's PbI2. And then what we're going to have after that, the sodium is going to combine with the nitrate from the left-hand side. So we've got NaNO3. Now this time we don't need to put parentheses because the charge on sodium is +1 and the charge on nitrate is -1, so it cancels out just like it is. Okay, we've got one more type of reaction that we're going to look at, and this type of reaction is actually called a combustion reaction. So let's write that out. So combustion. So a combustion reaction is, well, let's make that a little neater. So a combustion reaction is exactly what it sounds like. You're combusting something, you're going to basically blow it up, you're going to burn it. So a combustion reaction typically involves things called hydrocarbons. A hydrocarbon is something that takes the formula of C, and I'm going to put an X down here because X can correspond to any number. You know, there are a bunch of different types of hydrocarbons. And then I'm going to put a H, and then I'm going to put a Y, because these two numbers can be the same, but they don't have to be the same, and sometimes they're not. So I'll just put an X and a Y to let you know that these numbers can be pretty much anything. So whenever you have a hydrocarbon, you've got hydrogen here and carbon here, and you put them in oxygen, you burn them in oxygen. Now oxygen is diatomic, so it's O2. You're going to get carbon dioxide, CO2, and H2O. That is your products of a combustion reaction. You always have carbon dioxide and you always produce water. The only thing that's going to be different in a particular combustion reaction is the actual hydrocarbon that you have and the number that goes in front of each one of the molecules. Okay, so if we do a real life example, let's take the simplest hydrocarbon, methane, which is CH4. CH4, if I combust it in oxygen, like I said, this is the same thing. So we're gonna see this same thing throughout. So we've got O2, and then our products are going to be CO2 plus H2O. All right, so like we said, the same thing. The only thing that changes is the hydrocarbon. And now we'll go ahead and balance this equation just for good measure. So I have one carbon on the left, and I have one carbon on the right. So those are even. I don't need to worry about them. If I look over to the left, I have 4 hydrogens on the left, and I only have 2 hydrogens on the right. So in order to fix that, and to obey the law of conservation of matter, if I put the coefficient of 2 here, now I've got 4 hydrogens on the right, and I've got 4 hydrogens on the left. So now if I look at my oxygens, on the left-hand side, I've got 2 oxygens here. If I look on the right-hand side, I've got 2 oxygens in my carbon dioxide, plus the 2 oxygens in my water, and 2 plus 2 is 4. So if I want to make this guy 4, all I have to do is put a 2 in front of this, and now this particular combustion reaction is balanced.